Today we're going to start talking about exponential functions. So an exponential function is a non-linear function in the form of y equals ab to the x. So far in this course we've been talking mostly about things that were causing linear functions, nice perfect straight lines. As the independent variable, which remember is our x value, changes by a constant amount, either adding or subtracting something, the dependent variable, the y, is multiplied by a constant factor, which means the consecutive y value have a constant ratio. Okay, so when we talked about linear, we would see some pattern of plus or minus numbers from both the y's and the x's to give us a constant rate of change. When we talk about our nonlinears, and in this case the exponentials, we're going to see a constant amount for the x's, but on the y's we're going to see a steady multiplied number. And again, notice that I said multiplied, not divided, and we'll see some examples of that in a moment. So identifying functions. Does each table represent linear or nonlinear? So if I was to look at this first example in this table, how do I see my y's changing? So remember, the word linear means a nice straight line. And basically what we decided was, can I find a slope? So if I look at the y values, can I find a change in y over change in x? Well, my y values are all changing plus 2. My x values are all changing at the same time, plus 1s. So this is definitely linear. It has a constant rate of change, or it has a slope. Now I look at the second one here. Now, when I first look at my y values, I might say, well, 4 plus 4 is 8. But then I see 8 plus 4 is not 12. So it's 8 plus 8 is 16. So then I have to look back and say, well, how else can I get all of these numbers to create the next number? Well, hopefully we can all see times 2 to create all those y values. So there's a constant factor that's being multiplied. Now looking at the x values, I need to see something also happening down here. So now we are seeing plus 1s. So up in the definition, remember we talked about how the independent variable is changing by a constant amount. So there are our plus 1s. And the dependent is being multiplied by a constant factor. So then we would have a times 2 over 1. So this is definitely nonlinear. And it's actually going to be called an exponential function. Okay. Now evaluating exponential functions. So evaluate each function for the given value of x. So the x we're given here is the number 3. So I'm just going to basically plug this in to figure out what comes out. So y equals negative 2, the 5 being raised to the third. Now we got to think about our order of operations, our GEMDAS. So the first thing I need to do is take care of the 3. So 5 to the third power. Now remember, a common mistake here would be I would say, oh, negative 2 times 5 is negative 10 to the third power. This third power gets done first in GEMDAS. I would do 5 to the third power, then I can take care of the multiplication. So 5 to the third power is going to give me 125. And so my final answer is negative 250. And again, 5 to the third power, if you're not sure, 5 times 5 is 25, times one more 5 is 125. On the next one, now we are raising this power to the negative 2. So here's what I'm going to do. I'm actually going to change the 0.5 into 1/2 because I hope that we remember a negative exponent is going to flip the base. So it's going to turn that base upside down to make it 2 over 1 and then turn the exponent to a positive. Now from here, I can then look at this as 3 to the 4th power, which gives me an answer of y to the 12th. It's important that we make sure that these exponents are not causing too much trouble. We want to make sure we're constantly getting the correct answers, because one of the things we're going to start doing is starting to make tables. So next, we're going to talk about graphing exponential functions. Now this first thing, it's a lot of words here, it's a lot of math here. Basically, we are talking about graphing this form, y equals ab to the x. So hearing about this vertical stretch or shrink by a factor of the absolute value of a of the parent function y equals b to the x. A lot of math stuff here, but basically what's going to happen is this a that's sitting in ab to the x is going to help us determine if our graphs, which will be curving, if they'll be going up or if they're going to be dropping. So when a is going to be a greater than 0, it's going to be lifting it up. If it's less than 0, it's going to be dropping it down. Same thing over here. Again, these will depend a little bit on what the b value is. We'll talk more about those as we get going further. So here we are now trying to graph when the b value is greater than 1. So we have a function f of x that's 4 times 2 to the x. So we want to first do is graph this. So what we're going to do is make a table. Okay, so I'm going to put my f of x, which we also know refers to y's, on the right hand side, and we're just going to make a table. So when we talked about linear equations, we talked about making at least 3 points. Well, when we do these, we probably need a couple more than 3, because we really need to see how the curve is working. So for this one, I'm just going to kind of start at negative 2. We'll focus on 0, the 1, and the 2. So we'll get those 5 points, so we can really get a good feel for what's happening on this. So when the negative 2 is our exponent, remember, that is going to take the 2, which is 2 over 1, and flip it upside down, turns it then into 1/2 squared, which is 1/4, and then 4 times 1/4 is 1. Then, when I move on to the next one, this time the negative 1 flips that 2 base over to becoming 1/2, which then 4 times 1/2 is 2. When I plug in the 2 to the 0 power, remember that's going to be 4 times 1, which is 4. When I plug the 2 to the 1st power, I get 4 times 2, which is 8. And lastly, when I plug in the 2 power, I get 4 times 4, which is 16. Now looking at my table, hopefully we can understand why this is the exponential function. On the f of x side, which is my y side, I see a constant factor, times 2, times 2, times 2, times 2. On the x side, I see plus 1, plus 1, plus 1, plus 1, plus 1. So these would be my ordered pairs. So what I'm going to do is I'm going to draw a graph here, and all my numbers are, all my y values are all going to be positives. So I'm going to kind of do my XY table graph a little bit more, not right down the middle. Okay, I need to get to 16, and these exponentials can be tricky, so you want to think about scales. So just so that we make sure we stay on, I'm going to do by 2's going up, but I'm just going to stay with the 1's at the bottom. Okay, so then when I start plotting my points, at -2, we have 1. At -1, we're at 2. At 0, we're at 4. At 1, we all of a sudden are jumping, and at 2, we jump way up here. So basically, what we want to do is we want to draw a curve. And it's not going to be accurate. There is no straight edge for this. Just as smooth as curve as we can to kind of represent what's happening. Now, there's something I want you to really notice here. So this one seems like it's going to start going straight up in the air. It's never going to go fully straight up in the air. It's always fading a little bit off to the right as it goes. And the same thing is happening down here. One of the dangers we have when we do this, we see a lot of times students start just drawing the arrow going down. Well, in this problem, this arrow is going to start even more so flattening out. But it is never actually going to make it to 0, or the x-axis in this case. So we got to be really careful that we don't draw our arrows like just fading down. We got to make sure that we're drawing them, and they will look eventually like they're on the x-axis, but they actually never quite make it to the x-axis. So that would be my graph. Now, comparing this to the parent function. So comparing this one to the parent function. So what is the parent function, you might say? Parent function would have been y equals b to the x. So if I think about all those same points that we just did, okay, in this case, the y function, because we have a base of a 2, would be 2 to the x. So basically the difference is I don't have this 4 out in front. So all my numbers are really just not times 4. So if it was a -2, it would be at 1/4. So I'm going to put it kind of on that spot there. If it was at -1, it would just flip over to be 1/2. If it was at the 0, it would be 1. If it was at 1, it would be 2. And if it was at 2, it would be 4. So the parent function would look something like that. Okay, so it's not climbing as steep. It's going to definitely have a different y-intercept. It has a 4 versus the 1. They both will be flattening out towards that x-axis at some point. Okay, so it's definitely not as steep. It has a different y-intercept. Now, describing the domain and the range. So let's talk about that. Domain and range. So the domain. We talk about the domain as all real numbers, and this is kind of the symbol we use in math. It's kind of like a double R, if you want to call it that. And this is a symbol for all real numbers because there's really no reason that I can't use any number. Okay? The range, I have to think about what is the range? The range are my y values, right? Those are the ups and downs. And what is my graph seeing? We just talked about how my graph is never going to make it to 0, and in this case, never going to go below 0. So in this case, I am only going to see things that are y is greater than 0. It might look like it's going to hit 0. It looks like it might go below 0. But this is never going to make it to 0, and it will never actually go below 0. So let's look at the next one. So again, let's make a table of values. So if I was to make my table, change the color up a little bit. Again, let's just use -2, -1, 0, 1, and 2. If I plug in a -2, notice that that negative is out in front of the parentheses, so it won't get affected by that negative exponent. So the negative exponent would flip over the 1/2 and make it a +2, and then still raise now to the +2. So that's going to give me a -4. Then if I plug in -1/2 to the -1, that's going to turn into, now it's a +1, -2. -1/2 to the 0 basically becomes -1. -1/2 to the +1 becomes -1/2, and -1/2 to the second power becomes -1/4. So again, we want to draw our axes. Now these numbers are definitely smaller to deal with, so I think I'm going to make this one a little bit more central, but we don't see any positives on our x value, on our y value, so I'm just going to kind of go like that. And then if I start plotting my points, -2, -4 would be right there. -1, -2 would be right there. 0, -1, 1, -1/2, 2, -1/4. And again, if I draw this smoothest curve as I can, and we would want to put arrows on both sides because it is going to keep going, my graph's going to look something like this. Now again, remember, our parent function of this one would look a little bit different. So the parent function of this one would be y equals 1/2 x. Right? It would take out that -1 in front. So 1/2 x for this one is going to look similar. The only real difference is, if you think about it, if -2 goes in, this is going to come up to 4, which I don't have spot for here. If -1 goes in, it would come down to a 2. If 0 goes in, it's a 1, and then it would be the 1/2 and the 1/4. So it's kind of doing a similar thing, except it's really the mirror image. You know, it's the reflected mirror image over the x-axis. And then describing my domain and range, we still would say my domain is all real numbers because I can plug anything in. But now looking at my green graph, I don't see any y values above or at 0. So my range would be y is less than 0. Okay? So to begin and graph a function that's in this form, y equals ab to the x minus h plus k. You can begin by graphing ab to the x. Then remember when we talked about our absolute value functions, that thing inside the absolute value helped us get pushed left and right horizontally, and the outside plus k number pushed it up and down. Well, it's very similar to that. So this h on the inside, which says x minus h, is going to be my horizontal translation, and the k, the plus or minus, is on the outside, and then the k, which is going to tell us our vertical translation. All right, so let's see another example. So we want to first graph 4 times 2 to the x. Then we're going to translate this to going up. Okay, so we could certainly just kind of do the exact same. We could make a table and just go from the beginning, or we could do the steps that are here. So I'm just going to follow these steps here. If you can, just pause the video to draw the 4 times 2 to the x, and then turn back on so we can see what it looks like. So here was the 4 times 2 to the x function. So now when we see, same similar thing with the absolute value, this is telling me my horizontal translation. And remember we said in the absolute value one, if it's a minus number, it's actually pushing it to the right. Normally we think of subtract as going to the left, but it's the opposite. And then this outside number, this plus 2, is telling us that we're going to go up 2 units. So if I was to now draw this new graph, basically all of these points that I just plotted are going to translate 3 to the right and 2 up. So if I just take each point, 1, 2, 3, up 2, there was that first point, 1, 2, 3, up 2, 1, 2, 3, up 2, 1, 2, 3, up 2, and then unfortunately this last one, 1, 2, 3, is going to be somewhere up there, okay? But if I was then to reconnect this graph, I want you to notice something that what I just did. Notice that I'm not coming all the way down to the the x-axis. Notice that I'm kind of leveling off at 2. Basically, by the fact that the first function here, kind of approaches 0 but doesn't really get there, the fact that we then push it up 2 means it's never going to quite make it to 2. And it's important that we notice that so we don't always just draw it to the x-axis. Okay, so when I go to answer this time about domain and range, we're going to still say all real numbers. We're good with that. And then this time our y values are all, on my blue graph, greater than 2. I'm never going to get below 2, and I'm never actually going to go to 2. It's just going to be always a little tiny itsy bitsy bit above 2. So now we're talking about comparing two exponential functions. So in this problem, let me just read through this first. An exponential function g models a relationship in which the dependent variable, so remember the dependent would be my y value, is multiplied by 1.5 for every 1 that the independent variable x increases. Graph g, when g of 0 is 4. So remember, that's our function notation. That tells me that 0, 4 is our function. Okay, so then we are asked to compare this function and the function f from example 3 over the interval of 0, 1, and 2. So I'm just going to do this real quick here. So my function g, 0, 1, and 2. And then let's do the function f in blue over that same time, 0, 1, and 2. So that function f, so f of x, that was, remember, the 4 times 2 to the x. And we don't know what this one is, but we do have some information, and we'll look at that in a second. Okay, so remember back to the f function, when we plugged in 0, that made the 2 become a 1, times 4 made 0, 4. When 1 went in, 2 to the first is 2, made it an 8. When 2 goes in, 2 to the second power is 4 times 4 is 16. Okay, so I have to get up to that 16. We got to keep that in mind. Okay, so I'm going to kind of draw again. We don't see anything that's negative, so I'm going to kind of put this thing in here. We'll go by 2's again. Now if I plot that blue graph, 0, 4, 1, 8, and 2, 16. Kind of looks like a straight line, but we know it's not, right? It would be doing something like that. Now let's look at this G one. So we know that the y values are going up 1.5 each time. We also know one of our ordered pairs because it told us when G of 0, it equals 4. So when the 0 goes in, there's your 4. Now, if I think of my times 1.5, now I know that my next one would be at 6. And if I again do times 1.5, it would be at 9. Okay, so then this one starts out with the same y-intercept. But then at 1, it's only a 6. And at 2, it is only at 9. So it's definitely going to do the same kind of thing down here, but we can see that it is definitely not as steep of a rise. So that would basically be the reason that what's happening is it doesn't climb as steep. It would have a smaller ratio of things changing. And again, we can see that right here. Remember, these were going up times 2s, where this one is only going up times 1.5. So it's a more gradual exponential graph. And last one. So here we're looking at a graph. It's already been made for us. We want to write the exponential function of this that represents the population. And then we're going to use that in a moment. So first we want to remember, how am I going to write one of these things? The exponential function, we said earlier back at the beginning of this, is y equals ab to the x. So let's talk about what these a's and b's are. So basically, A is telling us our y-intercept. It's basically going to tell us where we would be crossing. And if you think about it, in this graph, we are crossing at 0, 3, right there. Now, looking at the graph, you'd say, no, it's crossing at 0, 0. But again, it doesn't ever actually, these things get closer and closer and closer. But the ordered pairs are telling us it is crossing at 3. So I can already start to plug in. A is my y-intercept. Okay? Now, the b. B is that factor that we keep seeing multiplied over and over and over again. So where do I see that happening? That's on my y values. So if I look at my y values inside the graph, I see 3 times 4 is 12. 12 times 4 is 48. 48 times 4 is 192. And 192 times 4 is the 768. So that would then tell me that we have a constant factor of a 4, and these are always being raised to the x. So just like with the y equals mx plus b, we always had x and y in it. Same thing here, the exponential function. The y-intercept would be the a, and that b is the number that we are multiplying over and over and over. It's that common factor that we're multiplying our y values. Now, how can we use that to help? So this last question, find the population after 12 hours. And then after 5 days. So let's think. Our labels are days on the graph. So 12 hours, we're not plugging in 12 for our x. We'd be plugging in 1/2. So I'm going to use my function and plug in 1/2. Now remember, in a previous lesson we just talked about these fractional or rational exponents. 1/2 is the same thing as the square root of 4. The square root of 4 is 2. And then 3 times 2 is 6. So that would represent the population of the bacteria after 12 hours. Then we also wanted to know 5 days. Well, the x's do represent days, so in this case, we're now going to plug in the x as a 5. And then 4 to the 5th power will give me 1024. And then times the 3 gives me 3072. So after 5 days, that would be the population of the bacteria. So a big part is starting to understand how to graph these exponential functions and using that y equals ab to the x, understanding how the different curves are happening, and also then starting to recognize towards the end of this one how a is our y-intercept and b is that factor that we are multiplying our y's by each time to help create the function so that we can use that to solve problems. There's a lot going on here. I hope you've had a good chance to get through some of it. Use these notes as you start to work on things, and please feel free to ask me any questions when you have them.